You are now live. Oh man, I need some energy now. Let's hope this coffee kicks in. So not a winter person.
Concussion wave alone will kill you. Here's the deal. At the beginning of the global war on terror, American forces were not ready to handle guerrilla warfare. Had light vehicles with little to no armor, and very few had turrets. If you don't know, a turret is this thing right here with the armor and the gun on top. 88 mics got shit done anyways. They would put sandbags on the floorboards of their trucks to provide some amount of protection to IEDs. They welded their own turrets on top. Because while the grunts are badass, they're still human. They need shit bricks, and they need water. And the 88 mics have a long history of giving them those supplies, regardless of what it takes. Because of the extreme danger that these men and women face, and the extraordinary lack of recognition for that danger, 88 mics in the Army are commonly referred to as 88 mistakes, also referred to as IED magnets. Now, along with having an enormous set of testicles, or ovaries, these men and women are actually really skilled. I would be willing to bet money that an 88 mic for a 35-31 could parallel park a fucking train. In conclusion, 88 mics have a long history of getting shit done, regardless of what it takes, and they deserve way more recognition for it than what they get. So here's to you. Thanks for watching. I hope you enjoyed it. If you enjoy my content with like funny and hear about it, there's a link for that right here. And there's also the link to my t-shirt. And there's also the link to my YouTube channel. If you're watching this on YouTube, that link is in the video description. I'm also working on getting hoodies and stickers. And this logo will be available soon as a water bottle decal. So until next time, thank you for your service. Quack bang out. Here we go.
Light green versus turn number one. Looks to be 331, I believe. It's going to be Adana Hauger. Nice shot.
This is probably going to come off pretty political, but I promise me being anti-bear. Okay, I'm just going to be honest with you. I don't like bears. Anytime bears are involved, it's not going to be a good time. Okay, the Chicago Bears, terrible football team. A bear market, that means the economy is doing bad. And then you have grizzly bears, which are absolutely terrifying. So when I wake up one day and this is in the headlines, obviously I'm going to get a little bit upset. Okay, it reads like I'm living in the Hunger Games. Basically, the Capitol is going to start systematically releasing grizzly bears near rural communities. I'm not about it. But like an adult, I realize the news headlines are pretty misleading, so I read the entire article, and it's pretty accurate. Basically, the federal government wants to release 7 grizzly bears every year for the next who knows how long into this area in Washington State. They want to get that number up to 200 grizzly bears. Which brings us to the obvious question, why? Why the fuck would you do that? And I have looked and looked for an answer to this, and as far as I can tell, the only reason they want to start reintroducing bears into this part of the country is because fuck it, bears used to live there, and bears are cool, I guess, is what their strategy is. Which, first of all, no, they're not cool. Okay, this isn't a fucking Disney movie. That's not Balloon talking about the bare necessities in the forest. That's a 700-pound meat missile covered in fur that can run 35 miles an hour that eats its prey ass first, okay? There's nothing cute about that. Do you understand the gravity of what I've just explained to you? Brock Lesnar weighed 265 pounds. He was the world heavyweight champion. This bear is equivalent to 3 Brock Lesnars running at you at 35 miles an hour. And to put that into perspective, Usain Bolt tops out at 27.5 miles an hour. Okay, the average American can't outrun heart disease. We're definitely not going to be outrunning fucking grizzly bears if it comes to that. And I can hear the comment section already. Huh, you know, actually bears are more scared of you than you are of them. Huh. No, that's not true. That's some shit your dad told you when you were 7 years old on your first camping trip, so you would shut the fuck up and go to sleep so we could bang your mom in a tent. Okay, that's not reality. And then you get all the environmentalist people, but you know, the ones that live way far away from this area, because environmentalists never advocate for shit when it's actually in their own backyard and it affects them. But they're going to say some shit like, oh, you know, the humans eradicated those kind, gentle creatures, and they used to live in that area, so we should really bring them back. No, okay, we used to have dinosaurs too, and there's an entire movie series about why bringing those back is a terrible idea, okay? Maybe we got rid of it for a reason. Have you ever thought of that? Because last I checked, the easiest way to get a city named after you on the West Coast is to get killed by a grizzly bear, and then they just name a city after you. And then we have to address the elephant in the room, because whether you're left, right, or center on the political spectrum, you have to admit that there was an extra layer of comedy in the fact that Joe Biden, of all presidents, wants to start releasing grizzly bears. Okay, look, I'm not a political analyst or like somebody whose opinion you should take very seriously, but I do think it's kind of bad taste to on one hand, be like, I want to ban powerful guns because I don't think people need them. Also, I'd like to start releasing grizzly bears indiscriminately. Okay, look, I don't ever want to get asked why I need a high-capacity magazine ever again. There's never been a better excuse to have access to a lot of bullets than the federal government colluding with grizzly bears. I mean, this has to be a joke, right? Like, somebody at the White House is just being petty, like, these goddamn gun nuts want the right to bear arms, we're going to give them the whole fucking bear. Okay, look, regardless of whoever's in office, whether it's a Democrat or Republican, all I'm saying is that the federal government can't do anything without fucking it up. Okay, this is a terrible idea. You know what, let me give you an example off the top of my head. In 1920, the United States government banned alcohol, okay? And overnight, every bar in the country either had to shut down or get turned into an ice cream parlor. So a bunch of them did. And then you have all these people who hang out with their buddies at the bar, and now they're hanging out at the ice cream parlor. So in many ways, ice cream filled the social gap left behind by alcohol. Got that? Okay, wonderful. By 1924, people didn't quit drinking alcohol as much as the U.S. government would like, so they decided that they were just going to start poisoning alcohol and giving it out to Americans. 41 of them died for sure. Some estimates go up to as many as 10,000 being poisoned. Okay, fast forward 1933, Prohibition gets phased out, but you have an entire generation of children that grew up eating ice cream every day because it was the social bond that held America together because it had replaced alcohol. So the United States government needed to have a bunch of milk because they were going off to World War II and all their soldiers loved eating ice cream and frozen dairy. This is why to this day every Navy ship has an ice cream machine on it, and it's like mandated by naval code or whatever. And because the U.S. government needed all this ice cream to feed their army, they needed a bunch of milk to make that ice cream with. And dairy farmers weren't even a thing yet because refrigeration had just come out, and it had never been feasible for one man to just harvest a bunch of milk from a ton of cows. It had never been done before in human history. And at first, it works out great. Okay, fast forward, World War II ends, the Allies win, the world is saved from the Nazis and the Imperial Japanese. Hooray. Now, the army went back home, they can buy their own ice cream, and these dairy farmers don't have anybody to sell all this milk to, and the government's not about to let the dairy industry get slack because they're the ones that convinced all these people that they had to become dairy farmers in the first place. So the government is like, fuck it, I'll buy all the milk. And then the government's like, what do we do with all this milk? And somebody says, hey, let's turn it into cheese. That way it can sit on a shelf for a little while without going bad. Then all this cheese started stacking up, and they're like, fuck it, we're just going to go hide it in a mountain in Springfield, Missouri. So that's what they did. They just kept shoving cheese into these caves every year. And every new president that came in, he had to sit through the briefing where they're like, yo, guess what? The U.S. government was buying all this milk, turning it into cheese. There's a mountain of cheese in Springfield, Missouri. In real life, it's a thing. And we can't stop buying the cheese. We don't know what to do with it. Then Ronald Reagan gets elected, and he's like, we're spending $1 million a day in refrigeration for a bunch of cheese that nobody's eating. We have to get rid of it. So he proposes to the U.S. people, hey, hear me out. I've got 500 million pounds of cheese. I want to throw it in the ocean. Okay, they get mad. They're like, no, we paid for the cheese. We would like the cheese at a minimum. You've taken our money. You turned it into cheese. Give us the fucking cheese. Okay, it's a relatable human emotion. So the government cut up all the cheese into 5-pound blocks and started handing it out to people. And this is where government cheese comes from. Okay, so that goes on for a while. Fast forward, Bill Clinton ends up getting elected. He's like, I have an idea about how to solve this milk cheese cave situation conundrum. I'm going to go to the FDA. I'm going to have them form an offshoot nonprofit company known as DMI. Dairy Management Incorporated, except this isn't going to be a nonprofit where like they give charitable donations. No, we're going to make it a legal requirement for every dairy farmer in America to give these people a portion of their money so that they can advertise for them because apparently milk and cheese isn't good enough on its own. Okay, if you're not picking up what I put down, I'm trying to tell you that the Got Milk ad campaign that was in every school cafeteria for like 3 decades is a government-funded psychological operation to convince people to drink more fucking milk because the U.S. government fucked up buying ice cream in the 1940s. And now they want me to not own guns while simultaneously trusting their ability to systematically release fucking grizzly bears.
That is just out of doubt the dumbest thing I've ever heard.
Okay, I'm done. I need a beer. I gotta go. Thanks for watching. Best way to support the channel. Go buy some merch at thefatalnutrition.com. Crack, bang, out. I'm probably never gonna upload this video, but we'll see what happens.
Good channel.
turbochargers. You gotta love them. In the first videos in this series, we covered the construction of a hybrid turbojet engine based on electric ducted fans with a compressor unit. The first video was sort of a proof of concept, and the next two videos produced a pretty successful engine. They made about 37 pounds of thrust and burnt a prodigious amount of fuel. Today, what I'm going to do is discuss the construction of an automotive turbocharger-based turbojet engine. If you go onto YouTube, there are dozens of videos about this subject, and if you go on Google, there are forums that will go into a great deal of detail. What I'm going to do tonight is I'm going to synthesize that information, and we're going to talk about the principles, the design, the assembly, and the operation of one of these turbojets. There are three major components to a turbocharger. There's the compressor, there's the center section that houses the bearing, and there is the turbine. Now, in both cases, there are turbine blades rotating in these two ends of the turbocharger. This is considered the compressor turbine. This is considered the turbine. Bit of jargon. But nevertheless, the same process is happening in both parts, just in reverse. The single most important number in sizing a turbocharger is what's called the inducer diameter. On the input side of any turbocharger, you have an aperture that allows the air to flow. The inducer diameter is measured at the narrowest part in the throat of this input. This is what allows the air to flow in. You want to be a little careful when you go on eBay or some surplus sites. They'll quote sometimes the outer diameter of this tube to make it sound like you've got a bigger turbocharger. However, this is the controlling factor in the induction of air. This number can vary anywhere from about a 20 millimeter diameter all the way up to monsters at 145 millimeters. The inducer will determine the amount of thrust you can make to control the amount of air. And as a rough guideline, if you do everything right, and I'm sure we probably haven't, you can expect to get about 10 pounds of thrust per square inch of cross-sectional area in your inducer, or 8 newtons per square centimeter. So the smallest turbochargers might make 8 or 9 pounds of thrust, and the largest can top 200 pounds of thrust. There's an enormous range. The other side of the turbocharger on the exhaust side is called the exducer, and it's the output from the turbine. In a normal automotive application, they want as little back pressure into their exhaust system as possible, so the exducer tends to be a little bit bigger than the inducer on the turbocharger. But in our case, we're going to want to convert some of that pressure into kinetic energy or velocity. And so we're going to want to put a nozzle on the end of the exducer to cause acceleration of the gas. Because there are a lot of variables, the RPMs that you're running at, the fuels you're burning, it may be difficult to calculate that, but as a rough guideline, you're going to probably start with an exducer at about 1.2 times the size of your inducer, and you're probably going to want to finish with a nozzle at about 0.9 of the diameter of your inducer. But to really nail it, one trick is that when you put your exhaust tube on here, either have a way to connect a throwaway component or make it extra long. And when you couple this on here and run the turbocharger up to its maximum settings, you can then take some sort of a clamp or a vise and compress this side to form an ellipse or an oblong shape. As you do so, you're reducing the cross-sectional area and therefore increasing the velocity. As you continue to do this stepwise, you'll reach a plateau where you maximize the thrust. At that point, you can take this piece of steel off or take the whole exhaust tube off, take it over a piece of graph paper, put your funny shape down there, trace the shape, whatever that ends up being. In this case, it's a rough circle. Allow for the wall thickness, count your squares, pi r squared, determine the cross-sectional area, and you'll know the diameter of a round tube that would give you that same area, and you have a nice formula for doing the taper. Or you simply leave it as an oblong. It looks funky, but it'll operate just as well. Now, beside the exducer and exhaust side, you have another important number, which is called the AR ratio, and that represents the relationship between the flow path, the area within the spiral for the compression and the expansion happening, and the distance from the axis of rotation out to the centroid of that flow path. Centroid is just a fancy way of saying the center of the area. In a circle, it's the center of the circle. In an oblong, it's the center point where the mass is flowing evenly about it. Here's a close to a circle, and basically what that means is that with a large AR ratio, meaning area relative to radius, with a large ratio, you have a rather compact turbo with a rather short distance around here. It will produce the least back pressure, and for a given inducer diameter, will have the highest flow to your turbocharger. It's best for the very high-end applications, like say drag racing and offshore racing, where at very high airflow rates, this will produce less restriction. On the other hand, because the radius in that case is small, you have a low moment arm over which that air is forcing the turbine around, developing torque compression. So with a very high AR ratio, it will be more difficult to start the turbocharger because you're going to have to get up to very high airflows before you get to a self-sustaining compression ratio. It also won't work very well at partial throttle settings. AR ratios vary between about 0.5 and 1.5, and it would be relatively conservative because maybe 0.7 to 1.1 if starting out, you want something that's going to compromise on both of those extremes. The third number is called trim, and it's related to the relationship or ratio between the diameter of the inlet part and the outlet part of the turbine to the actual overall diameter of the turbine. A small trim means you have a small area relative to the diameter, and therefore you have a much larger turbine that is accelerating the air. As you might imagine, with a small trim, you're going to have more compression, more speed in your turbine, but you're also going to have a lot more resistance flow. So just like the AR ratio, a small AR ratio and a small trim will tend to favor compression over airflow. And again, you probably want to pick a moderate number, somewhere around maybe 0.55 to 0.6 on the spec sheet for the turbocharger to be somewhere in the middle range. Now, the final issue is the bearing, the center section that contains the bearing. They can either be ball bearings, like steel or ceramic if you want greater longevity, and typically in the higher end, larger turbochargers, they will use ball bearings. They have higher load capabilities and they're more precision with all that additional rotating mass. But in the least expensive turbochargers and the smaller ones, they use what are called journal bearings. And basically, if you have a rotating turbine like this, there is a small brass or bronze insert with some flow holes that allow oil to pass from the housing tube into and through the bearing and actually force the bearing or the shaft inside of the tube. This is called a hydrodynamic bearing, and it's less expensive, it's less precise, but nevertheless it works very well for most applications, especially in the small turbos. In all cases, you're going to need cooling oil, whether it's ball or journal. And the oil is important because in this case it floats, in the other case the ball bearings will lubricate. The important issue about the oil, though, is that all bearings leak. They can't be perfectly sealed. And if the turbine is in good condition and the journal bearings are in good condition, the amount of leakage is going to be small. And it's simply going to be into the compressor or into the turbine and hell, it's fuel. So it'll burn just like the fuel would burn. And as a consequence, that's not the purpose thing. However, if the pressures inside of this chamber exceed the oil delivery pressure, you can get retrograde flow into your bearings, starve the bearings of oil, and destroy them. So it's important to make sure that the oil delivery pressure exceeds the pressure ratio that you're going to reach in a turbo. You'll rarely see these operating at above 30 psi gauge. And so you want an oil pressure that's somewhere above 40 psi gauge in order to make sure that you have a little bit of safety margin for the delivery of oil. In this turbo, though, you'll see that there are 4 tubes, 3 up here and then 1 sort of buried underneath it. And that's because this is a water-cooled bearing housing. Water cooling is available on both the small and the large turbos, and in most of the cases that we're going to be using this for, they're probably not necessary. It's probably possible for you to simply plug that off and ignore it. But the reason that they include water cooling in most of these turbochargers is because of the need to prevent a process called heat soak. When you drive these engines and you park a car or a truck, the exhaust has made the turbine side of the turbocharger extremely hot. And because you turned off the engine and you turned off oil delivery, what happens is the heat from the hot end will soak into the more thermally sensitive components in the turbocharger, potentially destroying them, coating the oil and destroying the bearing. So what happens, just like with aluminum engine blocks, there will be a continuous flow of water through the electrical water pump and electric radiator that will allow cool water to pass through both the engine block and the turbo housing to drain away some of that heat so that it doesn't damage the components. In high-end turbochargers, however, sometimes that water cooling is part of the design process to keep the center housing cool. So you can take a chance. If you have water cooling on the turbocharger, you can elect to plug it, or, as I've done, if it's included in here, we incorporated it in here, and so we have both water and oil cooling occurring. Now, the most time-consuming part of this project is the part that you have to do, which is the construction of the combustion chamber. The combustion chamber, if you go online, you'll find a bunch of different designs, but by and large, the most common is a cylindrical containment vessel that is essentially a pressure vessel. It's hooked up so that the compressed air out of the turbocharger is able to feed into the fuel entry end of the combustion chamber. And it's often mounted somewhat off-center on the combustion chamber to allow a vortex of rotating air to pass around the flame tube. This provides a more homogeneous availability of air so that you don't end up getting hot spots in the flame tube. Placing this off-center, typically the rule of thumb is you want it about halfway between dead center and where this side is actually parallel to the side. We're about 30% of the way over, but halfway is kind of what I've seen most recommended, and it's probably a very conservative number. When you move this way out, you start to get a very complex hole pattern for the welding, so that might be a little bit problematic. The size of the combustion chamber is pretty much defined by the size of the burn tube. The burn tube, which fits inside the combustion chamber, is surrounded by this annular gap, or the airflow. The length of the combustion chamber is determined by this length, and you want to make sure that it's large enough in diameter that it has at least half the spacing as the diameter of your inducer. So if you have a 30 millimeter inducer, you want to do 15 millimeters. You could make it enormous, but then you would add a lot of additional weight and expense. There's no need to do that. Now, one little thing I'd like to do is a little shout out to Agent Jay-Z. Anybody who really loves turbochargers and turbojets and jet engines at any time, the wonderful channel on YouTube, and he's got about 250 odd videos. And I want to say thank you because he has a great tutorial on wire locking techniques. And I went ahead and did that, and I think I got a very good result just following his recommendations. So just wanted to let him know and give credit for the information that he provided us. In any case, I want to talk a little bit about the flame tube. This is probably the single most complicated part of any turbocharger turbojet conversion. There's a lot of variables that enter into this, even like a fuse use. And the holes are designed to apply air, get air into the tube, and their spacing and their size are all based on chemistry. One of the most important things to understand about the burning of the hydrocarbon fuels is that there's a magic number called the stoichiometric mix. That is the mix where if you have an air-fuel mixture and it reacts, you do not have an excess of either component. All the oxygen is used, no extra fuel exists, it's the perfect mixture. It's the point at which the highest flame temperature is reached, because you're not adding any additional unused components that cool the flame. It's also the easiest flame to maintain, or maintain a flame point. It's the most stable. The problem with the stoichiometric mix is that as you add additional fuel or additional air, and it becomes more difficult to burn, you reach a point called the flammability limit, which you've gotten so much additional material in there that it won't burn at all. And as a consequence, you don't want to burn close to those limits. But if you were to burn the fuels at the stoichiometric mix, which is what you might think you want to do, you're going to end up with flame temperatures in almost all the hydrocarbons that are around 2,000 degrees centigrade, which would melt the turbine. Therefore, you have to introduce some additional material to cool it off. You could use extra fuel, but because you've got to carry that and you have to pay for it, you'd want to use air. And so what we need to do is introduce far more air than fuel needs to burn. But we also don't want to have that initially in one big blast, because we're going to have a very difficult time maintaining the flame front. And that's why we have the flow tube designed in such a way to these holes. These holes are called the primary, secondary, and tertiary holes. When the fuel exits the nozzle with a spark to initiate the flame, from this end of the tube, there's a large number of relatively small aperture holes that produce a lot of turbulent mixing of the fuel, but a relatively low airflow rate down through the tube gives the flame time to burn. As the flame continues to burn as it moves down here, it's probably a little overly rich. When you reach the secondary holes, then what happens is any additional fuel that may remain can get additional air added and is less sensitive to blowout or to flame out because it's already so darn hot in here. But the additional air ensures that you've got a complete burn, which then continues down here, and eventually that hot gas, if it's completely reactive, then has the tertiary holes pour another 50% of the air through them in order to cool the mixture before it enters the turbine and the blades exposed to the hot gases. While sizing and the spacings of the holes black art, but typically the diameter of the primary holes is half the secondary, and the diameter of the secondary holes is half of the tertiary holes. And whatever number of units you use to describe those holes, if you add up all the cross-sectional area of all these holes, they should equal the cross-sectional area of your inducer. Now the numbers of holes, typically 3 times as many holes in the primary section as the secondary and as the tertiary section. And there's a little bit of art to this, and so as a consequence, rather than follow the rule I just gave you, the numbers of holes that we put in this particular unit, which are 2.5 millimeters, 5 millimeters, and 10 millimeters, are about 90% of the cross-sectional area of the inducer, the idea being that if we are a little bit wrong, I'd rather add additional holes than to try to plug them. Also, when you buy this tube, buy enough to make a couple of them because you might mess up. If it turns out that when the burn pattern occurs inside, you take this tube out after some use, you find that you're not getting any heat damage or any heat effect that carries it down to these holes. You probably don't have enough holes up here, and you're not giving the flame a lot of time to react before it gets down here. So you probably have to add additional holes here. If it turns out that your flame is all up here, and as soon as you get down to about here, everything down here appears to be cool, then the reaction is forced to occur in only half the length of the flame tube. You've probably got too many holes here, and you probably don't have a complete burn. So you can add and subtract holes, you can vary the size of the holes in order to try to get a heat effective zone that begins here and continues nearly down to the tertiary holes. Now, if you want to get, something I forgot to mention, the dimensions on the flame tube are determined by the inducer. Typically, you want a flame tube diameter that varies between 1.5 times and 3 times the inducer diameter. So in the largest turbochargers, you can be closer to the 1.5 holes of the inducer diameter, and in the smallest, you want to be closer to 3. In this particular model, it's at 2.4. The length of the flame tube should be 6 times the diameter of the inducer, so 6 holes. If you follow those rules, you're probably going to have a successful build, but again, you may want to make some variations on the holes. When you're sizing the turbocharger, though, to determine how you're going to get it as efficient as possible, the single most important number is the compression ratio. And to illustrate that, I'm going to talk a little bit about thermodynamics.
The Cascade Platinum Plus, hello this, and that, air rotation differently.
Okay, this is a pneumatic cylinder, and if I plug the output from this cylinder, and I compress the piston into the cylinder, I'm doing work on the air within the cylinder. As I compress it, I've done work because it's force times distance. Even though the force varies during the compression, nevertheless, if you add up all of the little intervals of the force times the distance, I've done 1 unit of work. Let's just say that I compress the air to half its original volume. I've doubled the pressure. Now, what I do is I allow this to expand and do work on my muscles. I put 1 unit of work in, and I got 1 unit of work out. The force and the distance was the same. If, however, I compress the cylinder to the same point, and then I place it in a plane, and I keep the air within the cylinder, if I bring the temperature of the air up to twice its original temperature, so instead of 27 degrees centigrade or 300 degrees Kelvin, I brought it up to 300 degrees centigrade or 600 degrees Kelvin. What I've done is I've doubled the pressure inside the cylinder, and so then when I allow it to work against my muscle and expand, I get 2 units of work out, because at every point over that same distance, the force against the piston is twice as great. So 1 unit in, and when you heat it, 2 units out. Now if I do the same thing, but I compress it even further and bring the pressure up to 4 times its original level, and again, put it inside the heat source, and again, double the temperature. It's the same number of molecules of air, so it takes the exact same amount of heat to bring it to that temperature. But now the force, again, is twice what it was when I compressed it. So over the same distance, I have twice the amount of force doing work on my muscles. As a consequence of pushing it in harder and investing more in the compression, I get more of the energy of that same amount of heat back in energy, or back in the work. That's why when you invest more in the compression process, you get more out in useful work. And that's why diesel engines are more efficient than gas engines, because they have a higher compression ratio, maybe 20 to 1 instead of 10 to 1. Octane is a description of an 18 hydrocarbon, but it's also an adjective that's used to describe the resistance of a fuel to pre-detonation or ignition. Interestingly, high-octane gasolines actually contain less thermal energy than low-octane gasoline. But because they permit you to use an engine that has a higher compression ratio, they'll actually give you higher efficiency in the conversion of that heat energy into useful work energy. That is the reason why our original turbojet in the first series was so fuel inefficient, because it had a compression ratio of only about 1.3 to 1. A typical RC turbojet may have a compression ratio of, say, 3 to 1. You can achieve about 3 to 1 in a turbocharger-based turbojet. So you're going to want to end up running the turbocharger very near its maximum settings with the highest compression ratios. However, there's a limit to how hard you can run the turbine before it runs out of its tolerance limits. And so if you want to get even higher compression ratios and higher efficiency, there is a way to do that, and that's called series turbocharger. Effectively what you do is you take a second, larger turbo that you connect up to this turbocharger in series, so that the output from the compressor feeds the inducer of this compressor, and then this compressor in turn compresses the air further into the combustion chamber. So rather than getting a compression ratio of maybe 2.5 to 1, you get a compression ratio of 2.5 times 2.5 to 1, or 6.25 to 1. That much higher compression ratio adds to efficiency. It also means that because you have a denser air burning here, you can still continue to use a relatively smaller combustion chamber and flame tube, which saves a little bit on weight and compensates for the fact that you've added the weight of the second turbocharger. In addition, it's possible to bypass some of the air interstage, or intrastage, I guess it would be, to allow you to control the boost pressure over a broader range and give you more flexibility in the output at high efficiency. We'll get into that in more detail when we go to the next stage on this build, and we're putting the second turbocharger in series with this one. What I also want to cover is the support. In order to keep the turbocharger running, as I said, we need cool oil input and oil output, as well as the water flow that goes through these tubes. If we go down below, we'll see the systems that I got up to set up to do that. The oil drains out of the system into this reservoir tank here. At the bottom of that reservoir tank, you'll see a valve or a small port that allows the oil to drain out of the reservoir tank and into the radiator, where the oil passes through these pins, and the fans cool the air. This then allows cooler oil to flow up here and into the inline pure oil pump, which supplies the pressurized oil here
to the oil filter. The oil filter then allows clean, pressurized oil to flow up here and into the bypass assembly. What this allows us to do is by opening and closing this valve, we can control how much of the oil from the oil pump goes up into the turbocharger and how much is allowed back into the fluid loop to again reach the radiator and continue to circulate in a circle. And as a result, that allows us to have the additional flow beyond what the turbocharger may demand based on pressure to cool the inline pump, which requires a certain amount of minimum flow to keep from overheating. Finally, you'll see this little module down here where the oil temperature and pressure gauges are located, so we can monitor both of those on the device below this table. In addition, if you look in the back of the unit, you'll see a water pump, a radiator with a fan, and a water reservoir. And this simply circulates cool water to maintain the water cooling operation on the center section of the turbocharger. Finally, below this table, we have the diagnostics located here. The exhaust gas temperature reading that comes off next to the output near the booster, the boost pressure, the oil temperature, and oil pressure are all read on these gauges over here. Finally, this is a frequency counter. With these very small and very high-speed turbochargers, the turbine can rotate as much as 330,000 RPM. And at that very high speed, there is no way to measure the RPM with a contact method. You need to use something optical. And so what you do is you shine an LED or a laser in here, and then with a photodiode, you measure the pulses that's coming off, reflected off the blade. That pulse frequency is then interpreted by the frequency counter into an RPM. And that's important if you're going to be running the engine or the turbocharger near its limit to prevent it from overspeeding. Now what I'm going to do, once we finish the video, is I'm going to go ahead, assemble this into a complete unit. Then we're going to go outside, and in the next video, I'm going to run this thing up, I'm going to test it. I'll also explain to you why we decided to build such a small turbocharger for this first build. We've got some pretty interesting applications, and we'll get into that in the next video. So at this point, I want to say thank you very much for watching. Really appreciate it if you subscribe, because it does help out the channel a great deal. Alright, so the moment of truth. We're going to go ahead and show you how this operates. To begin with, since the first video where we showed you all the subsystems and components and design, we've added a couple of things that you'll notice that are important to get this thing operating. First of all, we have placed a high voltage spark generator to drive the spark plug to get the flame initiated. Once it's burning, this isn't necessary, it's just necessary to get everything started. In addition to that, you'll see a battery here that will drive a commercial 3-stage vacuum blower. The clean air that's provided by this blower allows us to start the engine up, as well as to be able to operate the engine or run the engine for a little while after the fuel's out of it, just to make sure that everything is cooled off quickly. That's a lot more convenient than using, say, a leaf blower or something that may have debris in it. You don't want to get anything nasty into the engine. In addition to that, what we've done is, rather than using a oil transfer pump, which can't generate the kind of pressure you need for operating the turbocharger, especially if you're going to go to 2-stage where you need 60, 70, 80 psi, we've actually opted to use an automotive fuel pump. It doesn't require you to kludge together some sort of a engine-driven type of oil pump with motors and belts and pulleys. And as long as you stick with a very low viscosity oil, this operates very well and is very convenient because it's also 12 volt. In addition to that, you'll also you'll notice that we hooked up the propane to be able to operate this. And finally, even though this is plugged into a cord, 110 volts here, everything on this system is 12 volts. We actually have a power supply in here that converts everything down. So you don't need 110 volt power to operate this. Everything will operate with 12 volts if you place this on a vehicle. Now the first step in doing this is I'm going to be turning on the power supply, and then I'll be turning on all of the motors, both the fans and the pumps. And once I begin the run-up in the operation, it gets very loud, so I'm not going to be saying anything. So you can watch what I'm doing. I won't have to do a voiceover in this case, because basically you're going to understand what goes on. First step is we're going to turn on the power supply to deliver power to the gauges. Exhaust gas temperature, boost pressure, oil pressure, and finally the oil temperature. We have not yet hooked up the photodiode of the hall sensor to the RPM, so that's why this one is off. We'll get to that in a future video. Now when I turn on this, you're going to hear a fairly loud volume as everything turns on. There's a couple bubbles in the pump, so you hear a little bit of gravity sound as that begins to disappear. You'll also notice the pressure is beginning to go up. And what I can do by adjusting the bypass is I can effectively control the pressure on the oil.
Kind of needs to be more smooth.
Now what I'm going to do is I'm going to crack open the propane here at the primary, and then I'll be controlling the throttle with the secondary here, the needle valve, so the fuel will go into the engine. When I turn on the blower, that's going to be about the last you're going to hear from me, so everything else is going to be visual. Here we go. Now, I'm going to let the oil pump and the water pump go for a couple of minutes just to reduce any kind of heat soak from the hot side of the turbine. But a couple of things before we finish here is that in order to measure the thrust output of this engine, it's kind of problematic, especially when we get pretty powerful and somewhat extended, to place this on sort of a rolling table. So our first attempt to measure the pressure involves using a deflector plate that we put in front of the engine with a pressure gauge or a force gauge mounted on the back side. We found all this ended up doing is producing a lot of cooking of the operator because of all the reflected heat that came back off the engine, so I didn't like that method too much. We're going to do an improved method for measuring the thrust by using a deflector. Basically, we're going to place this deflector in the flow path from the engine like this and mount it on some linear bearings. And we'll measure the downforce that's produced by the engine as it enters into the reflector. The advantage there is no matter how powerful the engine gets, the force will be down and we're not going to have to chain this thing down to the ground to keep it from tipping over when we go to the more powerful engines. Finally, you might wonder why we started with such a tiny little turbine. Because the smaller the turbocharger, the more difficult it is to get it to operate. The bearing resistances are pretty much the same no matter how big the turbocharger, so you have a bigger overhead in running a smaller turbocharger. In addition, the precision and the placement of the flame poles are very, very critical because you don't have a lot of time for the flame to burn through a small combustion chamber. The reason we did that is we have absolutely no intention of running this engine as a thrust engine. This is solely to produce high-pressure gas to drive a large free turbine to allow us to produce transmission or rotational output as well as drive a generator. And we wanted the smallest unit possible to make it potentially useful for more applications than some enormous vehicle. So as we'll show you these additional modifications and the progression with subsequent videos. But this is very exciting, and it's a lot of fun to come out here and just turn the thing on and annoy the neighbors and wake up my wife. But in any case, I'm having a ball with it, and I hope you enjoy it. So I'll be seeing you soon. I really appreciate you watching. Please subscribe. And for any of our Patreon followers, I appreciate that because that has been a real advantage to this channel ever since we did the last video on our 100,000 subscribers.
To give your teeth a sense of clean feeling, start with a round brush tap, add power, and you've got oral base.
Now, if you happen to have a turbojet, or you're thinking of buying one, or if you watch our video series on this subject, we'll show you how to build one. You really might want to consider adding an afterburner. These little devices can add a substantial amount of thrust for relatively low weight, low cost, and ease of assembly. It's a pretty good thing. Now, not all jet engines are turbojet engines. There are pulse jet engines, pulse detonation engines, ramjet engines, and even the very first forays that were made into the construction of commercial scale turbojet engines were done a little bit before World War II. They took powerful gasoline engines to drive the compressor stages that compressed the air before the fuel was added, and they produced the exhaust blast. And our very first videos on the jet series also used a hybrid type of design where we took some powerful EDFs, or electric ducted fans, about 5 kilowatts each, placed them in series, and produced a modest level of compression before we added the fuel, heated the exhaust, and nearly doubled the output from the fans alone. It really worked. designs is the enormous amount of energy that's necessary to drive the compressor stages. Just to give you an idea of the magnitude of that power, if you look at the Allison 250 series of turboshaft engines, these are small turboshaft engines that have been around for decades and produce a rotary mechanical output being driven by the exhaust gases by a turbine, and can range from about 350 to about 900 shaft horsepower. In those engines, the turbine stage actually sends only 1/3 of the amount of power that's extracted to the output shaft. Twice as much power as you take out is actually recirculated to drive the compressor stages, and that's a small engine. Another example is this turbocharger over here. This single stage compressor, just this little part of this turbocharger, at full power will consume about 250 horsepower from just this little thing. The power is enormous. And so that's why early on the military designers decided to take the hot, high-pressure, high-velocity exhaust from the jet engine, run a turbine, and send that power to the compressor stages. It was lighter and more powerful than the gasoline engines, and hence the birth of the modern turbojet engine. We decided to make the same sort of transition and got away from the hybrid design and started building jet engines based on the turbocharger to turbojet conversion. Now this is actually a pretty popular project, and there's a lot of YouTube videos out there about it because it's relatively easy to do. Because there are millions of these turbochargers built every year, all of the expensive engineering, the design, the precision machining of the compressor wheels, the turbines, the housings, the bearings, is spread out over millions of examples. And so all you really have to do to construct the turbojet is to build the combustion chamber. It's not trivial, but it's a heck of a lot easier than the other components. And if you watch our videos on the subject, we show you how to do it. Now, what makes building an afterburner possible is that all turbojet engines pass substantially more air through them than they actually need to burn the fuel. The reason for that is that if you take that ideal mixture, that golden ratio or stoichiometric ratio of fuel and air, and you burn the fuel so that you use up all the oxygen, you use up all the fuel, and at the end of the reaction there's nothing left behind, you produce a flame temperature that is so high that you would almost instantly melt anything downstream of the flame. So what the designers do in a turbojet is they take the compressed air that comes in from the compressor, they send some of it into the combustion chamber to burn the fuel, and then as those very hot exhaust gases are moving down toward the turbine, they allow additional air to dilute that hot flame, more air than was actually needed to burn the fuel, to bring the temperature down to the point that it will not melt the turbine blades. This is great because what ends up happening is at the end product of a turbojet process, you still have a substantial amount of oxygen in the exhaust gases. However, you not only cool the air by dilution, but the amount of energy that's taken out by the turbine stages causes a lot of cooling, shrinking, and decrease in pressure of the gases that are coming out of the exhaust stage. So what the afterburner does is it takes advantage of that residual oxygen, it adds additional fuel, and reheats those exhaust gases. It can double or triple the volume of those exhaust gases. It's often called a reheater or an afterburner, same principle. By increasing the volume of those gases, if you don't increase the diameter of the duct through which they're passing too much, the only way for that much larger volume to get out is it has to get faster, it has to accelerate. And when you accelerate the same mass of air, you increase the momentum, mass times velocity. And momentum is another name for thrust when you're talking about turbojet engines. This is great. I mean, when you think about it, it's lightweight, it's easy to build, there are no moving parts, and because you can fabricate these such that there are no metal contact to the flame, you can go to extremely high temperatures in the afterburner. So you might think then, why aren't afterburners put on all jet engines? The problem is very low fuel economy. you can double the fuel flow in an afterburner, double the fuel flow that you're normally using in a basic turbojet engine, and increase the thrust maybe 60 or 70%. And that might be acceptable if you're trying to take off from a carrier deck or you're in a combat maneuver. But if you're flying a commercial jet across the Pacific, you're going to probably end up in the water. Now, the reason for that is not because the afterburner fails to burn all of the fuel. It does. It's an efficient way to burn the fuel. The reason for this is a fundamental physical property that is inescapable, and it's present in the operation of any kind of internal combustion engine, and a jet engine is an internal combustion engine. This principle is so important that even though I reviewed this some time ago, I'm going to go through it again because I think it'll help to understand what I'm talking about.
Bounty Mega Roll, 4 rolls in 1.
If I take this air piston here, and I plug the output hole from this, and I compress the gas inside of the cylinder, my muscles are doing work on the gas inside the cylinder, force times distance. If I allow the piston to move back, the gas to expand, the gas does work on my muscles. 1 unit of work in, 1 unit of work out. No big deal. If, however, I take this piston and I compress the gas to twice the pressure, then I place it in a heat source and begin heating the gas to twice its absolute temperature. So if it's 300 Kelvin, it goes to 600 Kelvin. If it's 0 degrees Celsius, it goes to 300 degrees Celsius. At that point, the pressure of the gas molecules inside roughly doubles. Now when I allow it to expand, the force at every point in that expansion is twice as great as it was when I compressed it. So I get 2 units of work out. 1 unit in, heated up, 2 units out. 1 net unit of work. Okay, do it again. But this time I push the cylinder in much harder and I bring the pressure to 4 times its original level. Now, again, I heat the gas. Same amount of heat, same number of air molecules, and I bring the pressure up to roughly twice its original point. Now when I allow the piston to move back, it's moving farther and at greater force, and so I get 2 large units of work in. The point being that the more work you invest in the beginning, in the compression stage, the more usable work you can get out at the end. You physicists out there, yes, I am rounding off some of the ideal gas law numbers, but the underlying principle remains. More compressive work in, more usable work out. And this is one of the reasons why a diesel engine is more efficient than a gasoline engine. A typical gasoline engine has a compression ratio of maybe 8, 9, 10 to 1. A diesel engine, maybe 18 to 20 to 1. And a high-performance turbojet engine can exceed 50 to 1, 50 to 1. It's a very efficient heat engine. And that's what the problem is with the efficiency of an afterburner. Because the turbine stage has removed a lot of work energy from the fuel, from the gas, the pressure drops inside of the afterburner. And so when you're adding the fuel, you're adding it at a lower compression ratio than when it's burned inside of the turbojet. There's no way to avoid that. But if you want to take off from a carrier jet deck, it's the way to go. And if we really don't care about fuel prices, you know, they're as low as they're ever going to get right now, then we don't care either. We just want more power. So with that basis in physics behind us, let's go outside and let's fire up the turbojet engine. All right, this is the turbojet, and as you can see, it looks pretty complicated. You could put down your paper and your pencil. If you're interested in designing something like this or using some of the ideas that we have, we're going to follow this video with a series of short, few-minute videos that are going to break this down into all the subsystems, including the source for the parts that we're using and how we build this and how we operate this. So for today, you can just watch me go through the abbreviated startup sequence and enjoy. So let's get going. All right, let's get some headphones. Now we're going to start by turning on the oil pump and the fuel pump. We're going to adjust the oil pressure to about 40 psi. And the fuel pressure to about 50 psi. Now when I turn on the starter fan, everything is going to get so loud, everything will have to be in text boxes. You're not going to hear me. All right, here we go. All right, one of the nice things about having the starter fan on here is that when we're done with the run, rather than waiting an hour for this thing to cool off as it radiates heat, we can run this at a low level for about 10 minutes and we can exchange parts. So I'm going to do that right now. Okay. Okay, so now let's get into the nitty and the gritty of the actual afterburner design. Now, this is a nozzle. I took this off the jet engine that we just demonstrated. And almost invariably, you're going to want to have a nozzle on the output of any kind of a turbojet engine. The reason for that is that the exhaust gases that come out behind the turbine, or in the case of a turbocharger, from the exducer, are still under some residual pressure, and you want to convert that pressure into greater velocity. What the nozzle does is just like putting your thumb over the end of a garden hose, it causes the gas molecules to speed up, more momentum, more thrust. Now the design of a nozzle is, in theory, pretty difficult to model because there are so many variables. It depends on the AR ratio of the turbocharger. This is a value that determines the mass flow versus compression ratio of a particular model, and it varies. It also depends on what kind of pressures you're running inside of your combustion chamber, even the bypass ratio and the fuel that you're using. Pretty difficult to model. But in practice, it's actually very easy to do. What you do is you obtain a flange that will mount onto your turbocharger and then place a rather aggressive taper on the output. Aggressive being that if you start with a ratio of 2 to 1 in area, so not diameter, but the area of the output is half the area of the input, this is almost certainly going to be a little too much. Once you've fabricated that, bring it out to the engine, connect it up, and run it up. Measure your fuel flow, your pressure, your thrust, your temperatures. Then take it off, bring it inside, and slice a couple of millimeters off, opening up the aperture just a little bit, and test it again. Do this several times until the numbers that you care about stop getting better. You're done. It's that easy. And it might sound like a little bit of work, but it's fun because that's why you built the turbocharger in the first place into a jet engine. You want to mess around with it. Now, the afterburners themselves are relatively easy to build because of the fact that there's so much aftermarket availability of compatible components to turbochargers. You can get flanges of different sizes and styles, T3, T4, 4-bolt, flares, tapers, tubing, that all sort of work together. So that all you really have to do is cut the tubing, drill some holes, and do some welding. It makes it a lot easier for you to do, simply because you don't have to fabricate the tubes. Now, the designers of a military afterburner face much bigger challenges, because if you're going to put an afterburner on a fighter jet, you want it as light, as compact, and as efficient as possible. You don't want a huge stovepipe sticking out of the back of a fighter jet. The problem is that turbojet exhaust velocities, even in our little turbojets, approach Mach 1. And so literally you only have a few milliseconds for all of the fuel to be added, mix and blend, evaporate, burn, and expand before it gets out of the exhaust duct. That's tough. And it has to happen inside of the afterburner. If you have the burn continue outside of the afterburner, it may look cool.
My battery's
It may
going.
look like a nice
I gotta
glow
go.
torch,
My
but it
battery.
does nothing because all of the expansion of the gas is happening in the atmosphere. It has to happen in the confines of the duct in order for that velocity to accelerate.